Welcome to the Rapid Revolution. Today, we will explore how the lithium used in our everyday batteries is mined. But things are starting to shake up a bit, so we will also explore a new mining technique that could disrupt the entire lithium supply chain. This disruption could drastically lower the price of lithium-ion batteries, propelling the electric vehicle and smart grid revolutions. Used in a variety of batteries, the vast majority of lithium is mined in Australia, Chile, and Argentina, but the world is hungry for more lithium-ion batteries than ever before. Lithium demand could potentially triple by 2025, but will the mines be able to keep up? Let's first look at two major lithium mining methods, discuss their pros and cons, and see how scalable they are. Later on in the video, we will look at the new lithium mining method that could potentially disrupt the entire lithium industry. First, we will explore how lithium is recovered from liquid brines, pumped up from underground reservoirs. In places like Chile, Argentina, and Bolivia, sometimes called the Lithium Triangle, liquid brines with relatively rich concentrations of lithium are pumped to the surface into evaporation ponds. The liquid brines sit in these evaporation ponds for anywhere from 8 months to 2 years. As the sun evaporates more and more water, the lithium stays behind in the pond and continues concentrating more and more. Also, some other salts like sodium and potassium chloride begin to solidify. Eventually, the brine ponds reach a high enough lithium concentration, and the lithium-rich liquid is pumped to a processing facility to recover the lithium for sale. After reaching the lithium extraction facility, the brine is run through chemical treatments using lime and sodium carbonate to remove undesirable minerals like magnesium, sulfates, and calcium. Afterwards, the brine is treated again with sodium carbonate, also known as soda ash, at temperatures around 90 degrees Celsius to form lithium carbonate. Afterwards, the lithium carbonate is filtered, dried, and packaged for sale. On the pro side, prospecting and developing the lithium brines are cheaper because the land is flat and easy to get to. Also, drilling to the underground reservoirs is easier because the ground is relatively soft near the surface, and the reservoirs are pretty shallow. On the processing side, moderate temperatures are used, and the chemicals used for treatment are widely produced and relatively cheap. However, on the con side, the brines must sit in evaporation ponds for extremely long times and taking up vast amounts of space. Furthermore, not all areas of the world are at the right elevation and humidity levels to take advantage of evaporation by the sun, so this method has been mostly limited to Chile and Argentina. Ultimately, brine mining will be hard to scale to other areas of the planet, but could grow in the hot, arid regions of Chile and Argentina to help satisfy the growing demand for lithium. Now, I mentioned two methods of lithium mining dominate, and the second is mining spodumene, a hard rock rich in lithium. Currently, mines in Australia lead the way in worldwide lithium production with Talison Lithium's Greenbushes mine. Located in a fairly flat region of Australia near the southwest coast, the Greenbushes mine has a hard rock rich in about 50% spodumene, with about 3.9% lithium oxide. However, the lithium in this hard rock is a little harder to extract, and the operating costs for this method are about twice that of brine extraction. After the hard rock ore is mined, the ore is crushed and grinded, ran through a series of froth flotations, and then dried in a rotary kiln. After this, the ore is roasted at about 2012 degrees Fahrenheit and cooled to 150 degrees Fahrenheit. Then it's crushed again and roasted again with concentrated sulfuric acid. After this second roast, the lithium sulfate is formed. Finally, some hydrometallurgical conversion steps convert the lithium sulfate into lithium carbonate or hydroxide. In a previous video, we saw some hydrometallurgical conversion used to recycle batteries, so maybe there are some similarities. This may sound like a pretty complicated process, but the demand for lithium is high enough that this more expensive process is still worth it. Additionally, extracting the lithium from spodumene happens much faster and doesn't require waiting for up to 2 years for the sun to do its work. However, Chile has about 3 times the reserves of lithium compared to Australia, so maybe Australia will run out first. Or maybe not. The cost of prospecting and discovery when looking for lithium-bearing spodumene is more expensive than brine mining exploration. With tougher terrain, geophysical surveys, diamond core drilling, resource estimates, finding spodumene is a little bit more involved. And don't forget that metallurgical tests must be done on the ore samples to determine if commercial level extraction and processing will even be economical. All in all, the capital cost to get a spodumene mine into production could be about 6 times the cost of starting a brine operation. Despite this though, the Greenbushes mine, the premier Australian spodumene mine owned by Talison Lithium, is going to have some contenders. For example, the Pilgangoora project, started in 2017 by Pilbara Minerals, is expanding its operation to meet the growing demand from Chinese and South Korean markets. In addition to these two projects, Orocobray's Olaroz lithium facility, Galaxy Resources' Mount Catlin operation, and Altura Mining are a couple of the other players in Australian lithium mining. These projects could rapidly expand as the demand for lithium-ion batteries begins to exponentially increase. However, if all these hard rock spodumene projects or brine operations scale up, they will still have their inherent problems. Brine mining will still be slow and hard, and rock mining will still be energy intensive. But what if there was a better way? Here's where clay mining comes into the spotlight. Clay mining is promising in a couple of ways. Clay is softer and easier to mine from the ground than hard rock. Clay minerals contain lithium, which can be extracted using fast hydrometallurgical conversions. Clay minerals don't have to be roasted at extremely high temperatures to break out the lithium. And also, clay minerals are found in lots of places, including the United States. Recently, Tesla announced that they purchased about 10,000 acres in Nevada for mining lithium. But before we discuss this, let's talk about some work done in the area first. Cypress Development Corp and a few other players have been messing around with lithium clays for a couple of years. In 2018, Cypress reported that they were able to extract about 75% of the lithium from claystone samples by leaching it with dilute 5% sulfuric acid and heating the solution to 80 degrees Celsius. This is much lower than 2012 degrees Fahrenheit, even if you don't know the conversion off the top of your head. Additionally, they see opportunities to improve extractions by changing the leaching conditions, so they should get a little bit better at this. However, a couple things need to be noted about extracting lithium from clays. Previous testing by Cypress confirmed that water leaching did not produce a lithium-rich fraction, so chemicals and hydrometallurgical conversions are necessary. Additionally, the type of claystone does make a large difference in the cost of extraction. For example, American Lithium reports that hectorite, a soft white clay mineral pursued by other mining operations, is relatively hard to extract lithium and requires roasting. By targeting a different clay variant, lithium held in a weaker bond is far easier to extract. American Lithium plans to develop custom hydrometallurgical processes to leach the lithium out of the clay, no roasting required. Their Tonopah Lithium claims could begin mining lithium ore at ground level with easy extraction, no water contamination issues, or pesky toxic metal impurities in the clay either. They're about 4 hours from the Tesla Gigafactory, so they are close to their customer. However, let's now shift our focus to Tesla. At their Battery Day event, they didn't provide a ton of details about their lithium mining operation, but basically, they have a ton of land in Nevada somewhere, they plan to extract clay, leach it with diluted sodium chloride, otherwise known as table salt, into a sodium chloride solution. They will pioneer this hydrometallurgical process and use it to extract lithium from the dirt or clay that they mine, while skipping the lithium sulfate step. Afterwards, they will put the dirt and clay back. So what else can we figure out about what Tesla is up to? Most probably, Tesla will target an easy clay just like American Lithium. By doing so, they can develop their own hydrometallurgical process and skip the roasting step as well. Since Tesla is looking to halve the cost per kilowatt hour of lithium-ion batteries, this will be their starting point. By using sodium chloride, they will avoid producing lithium sulfate, which normally happens when using sulfuric acid. Additionally, the sodium chloride solution will be able to leach a significant fraction of lithium from the clay. After this, perhaps a reaction with water will convert their lithium extract into a lithium hydroxide, which could then potentially be used directly in the production of their batteries. They are designing their own cells with their Roadrunner project, so the possibilities are kind of up in the air. After producing their desired form of lithium, they will recycle their process water for extracting more lithium. Ultimately, extracting lithium from clays may disrupt the entire lithium mining industry for a couple of reasons. Mining soft clay at the surface is easier than hard rock mining. Processing lithium clays eliminates energy-intensive roasting steps, and by using dilute acid solutions, it lowers the cost of treatment chemicals. Additionally, hydrometallurgical conversions of clays occur quickly in a matter of days, not months. Lastly, Tesla has the necessary capital to start an ambitious project and the track record of disrupting traditional industries. If I was any other lithium mining company, I would be a little bit nervous right about now. That's it for today. I hope you learned about the current state of the lithium mining industry, the baby steps taken to start mining clay, and some explanation of how and why Tesla could entirely disrupt this industry. Stay tuned as the industry changes, and stay tuned for more RapidREV videos. Thank you for watching this RapidREV production. Please drop a like and subscribe. I'll be doing a giveaway for my subscribers once I reach 10,000 subscribers, so comment, like, and subscribe to enter. Thank you for all the comments. I really appreciate the words of support, the appreciation, and also the insight that you guys are providing in the comments, so keep it coming. For today, leave a comment about whether do you think lithium suppliers will be able to meet the demands of battery electric vehicles and grid storage? Will localized lithium mining and supply chains accelerate the sustainable energy transition? Drop your thoughts below. Also, if you want to talk about technology more, check out the Discord and come join the revolution. We have had a ton of people join, are having some awesome conversations, and are keeping up with stuff like SpaceX launches, Tesla news, and other things. So if you enjoy talking about technology and anything else like that, come join the Discord at the link below. Also, if you want to check out RapidREV on Twitter and Instagram, the links are in the description as well. If you enjoyed this video and want to support the channel more, head over to the Patreon and show RapidREV some love. All donations help make this content possible. Thank you to Adam Kennard for being the first patron. Anyways, that wraps it up for today. Come hop aboard the revolution, and I'll see y'all next time.